So here we go with the this exercise number 2, the calibration of effect sheet fracture permeability, and this is probably may look like a trivial problem, finding multipliers, but it's something that in fracture reservoirs sometimes if we don't have the right tools, we have to do it. We have to spend a lot of time modeling with discrete networks and then modifying the models. So here is the problem that we're facing is that when we model P32, the fracture intensity area per unit volume, that number is typically unitless. And is normalized between 0 and 1, but whereas real P32, as Jim explained yesterday, real P32 has units of meter squares over meter cube, area divided by volume. So we need to before we use these P32s that we are estimating, we need to convert them, okay, to the real units. So here is a model that we built, and we have one cell. We're going to do this exercise only in one cell of the model. And then in this cell, we have the orientation and counts from, let's say, from FMI data. That's the input data. We have a measured permeability, let's say, of 80 millidarcies. We have metrics permeability of 0.1 millidarcies. We have the orientation of SH max that is 100 degrees from north. And then we have the permeability that we modeled from the grid, either Petrel or GoCat or whatever software you are using, and that in that particular cell, let's assume that the model P32 is 0.6. So how do we normalize that? How do we change this unnormalized number to a normalized one? So we are going to use this spreadsheet that is here to do that. And this spreadsheet, what it does is that it basically solves the other equation. And so let me go into a little bit more detail. This is the model that we showed yesterday that has the P32. This is one of the examples that we showed in the Eagleford. And this P32 that we built yesterday is, as I said, is normalized between 0 and 1. So we need to put that in the right units. Then we're going to be using in the spreadsheet also, is internal in the spreadsheet, these equations that Jim presented yesterday that helps you, first, this is the equation for P32, and this is what is programmed into the spreadsheet for different fracture orientations. And then there are all these relations that you can get sigma from P32, and then you can relate the effective permeability that which is related to what you measure at the well. You can relate that to P32 by changing the hydraulic aperture of your fractures. So we're going to be using these equations. Also, this is kind of at the heart of the spreadsheet, solving the other equation. So the spreadsheet, you will have to input your different orientations in that cell, and then you have to make assumptions about the width, about the volume of the cell to calculate fracture porosity, and then it will give you the effective permeability. It will give you Kmax and Kmin, the orientation. I mean the values, and also the orientations of Kmax and Kmin. So that this is what the spreadsheet will do. And then with the spreadsheet, you will be able to solve or to recreate this figure that we showed yesterday, that we introduce different angles or different orientations of fractures, and then the output of the spreadsheet is, for instance, the Fisher coefficient that we are indicating here in black, and it's also the orientation of maximum permeability. Those are the outputs of the spreadsheet. Okay, so you will be able to recreate this figure for any fracture orientation that you have. And finally, the other aspect that the spreadsheet takes into account is the geomechanics. We discussed that fractures that are approximately 30 degrees with respect to the maximum horizontal stress, we use a multiplier for those fractures. they have a multiplier for the permeability. They have enhanced permeability, and fractures that are at 90 degrees, they have reduced permeability. The effect of stress is negligible, and then fractures that are in tension, they have another multiplier. So that's we also introduced that in the spreadsheet, and the idea is that we are able to recreate also this other figure that we showed yesterday, with that explains that takes into account the effects of stress on the permeability. So we will be able to put different fracture orientations, put the stress, and then see what happens when some orientations are more open than others. Okay, so here is so we're going to use this to solve this with the hold on, with this spreadsheet here. Okay, so here are you input here are the angles that you can use. This is the number of fractures that you would measure for different angles, let's say from FMI. Again, this is only in one cell of the grid. This is the aperture, that in this case all fractures by default we have 0.1 millimeters, and then we introduce the orientation of the maximum horizontal stress. We put these multipliers that I referred to, parallel to SH max, critical stress fractures, and perpendicular to SH max. We input the measured perm, the matrix perm, the area of the cell thickness, the fracture height. So with all these parameters, then we use the equations that I showed before, and then we create all these outputs. Okay, we create the variance or the Fisher coefficient, the orientation of the maximum anisotropy of or K max, the actual value of K max in millidarcies, K mean, the anisotropy coefficient K max divided by K mean, the effective permeability, which is supposed to this is what you model, what you try to replicate when you have a real measurement, and this is what we're going to do in this exercise. And then it computes other parameters that like P32, fracture porosity, all the parameters that Jim has been mentioning. We calculate all that with the spreadsheet. And something that we want to show here is that you can, by applying the concept of continuous model, you can do all these calculations without actually modeling a fracture, which is what you have to do this calculation if you use discrete models. Okay, so here is the exercise. So we have this cell area, and we're going to assume, as I said, I'm going to be going back and forth between the PowerPoint and the spreadsheet. So the cell is 3 meters height, so we're going to put here in the cell thickness, we're going to put 3 meters. It's already there. Then we have 3 fractures oriented 40 degrees. So here in 40, we're going to put a 3, and then it continues the exercise, and then we have 12 fractures at 130 degrees. So here we put 12 fractures. This is assuming that this is what we measure, let's say, from FMI in that interval. We're going to assume all the fracture widths are 0.1 millimeters, and this is what we have here. We're going to assume a permeability, a measured permeability from a well test, for instance, of 80 millidarcies. So here we're going to put 80. The measure perm, we're going to assume that the maximum horizontal, the orientation of SH max is 100. So we put here 100. And then clockwise from north. And then we assume that all stress multipliers, so there is no, let's say, stress effect. They're all equal to 1. So it's a simple question. Now, after you input this data, what is the model effective permeability? So all you have to do after you input your data is that you model you look at what is the result, and is right here. So this is the effective permeability in that cell that corresponds to those parameters. Okay, it's 41.225 millidarcies. So this part of the exercise is very simple. You simply input the data and you look at the number. Okay. But then this is what you're modeling, all right? But then what you're measuring is 80. This is what your well test. You measure 80. So that there is an issue here that what you're modeling is not what you're measuring. So you have to do something to your model to match your observation. So here in this plot that I haven't explained, here we have different parameters. We have these two bars. The red is the orientation of K-mean, and then here's the orientation of K max. The horizontal axis is our angles, strike angles. And then in blue, it's hard to see for this geometry, but you have the fractures there as well. And then there are two lines. This is the important part that I wanted to show for this part of the exercise. There are two lines, which all this is normalized. This is the measured perm, and this is the model perm. In this K effective, and this is the measure. So our goal is to start changing something in the model until we match those two. Okay, because we're having a model that doesn't explain the data. So the idea is that we go to number 2, modify the permeability multiplier for critical stress fractures until the model effective permeability is approximately equal to the measured permeability. So we have to do something to the multiplier. I mean, our model doesn't have enough permeability. We have to increase the permeability somehow. That means probably we start by increasing, let's say, the aperture of the fractures. Since we don't know, we cannot increase the number of fractures because that's a measurement. So we go for the parameters that we don't know. So we increase the aperture of the fracture. So we have to start changing those multipliers until we get something that is the same as the measure permeability. So it is telling us that, okay, go to the critical stress fractures multiplier, which is right here, and start changing that. So we're going to put, let's say, 1.1, and then it starts getting closer, the measure and the model. So we keep going, 1.2, and then it's getting closer. So we're going to put, let's say, 1.5. Then it's very close, and then we can keep adding numbers. And of course, since I already did this, I know that 1.56 is a very good answer. You can keep refining, but then what you see here is that this is what you measure. The measure permeability is 80 millidarcies, and this is what your model is, 80.3 millidarcies. Okay, so and you did that by basically changing the aperture of the critical stress fractures, increasing that a little bit more with respect to the other fractures. Okay, so now you have a calibrated model by doing this, and if you have information in different wells, then what you have to do is repeat this process in different wells, and then you are going to find different multipliers, or maybe the same multipliers, but generally they might be different from one well to another. Okay, so that's part 2 of the exercise. Then is part.
Can I ask a question?
Of course.
Yeah. I put the same numbers, and my model one and the measured one are close to each other, that they are perfectly fine, 80.2 and 80. But when I see your values for P32 and sigma, so mines are completely different. I have got P32 7.3 and my sigma is 27.3. So why there is so much difference?
Oh, okay. So maybe you can check that the numbers are the same in terms of the input data, and so probably something else should be different. I mean, I don't know exactly what you would be your input data, but they're supposed to be the same. Okay.
Yeah.
So if they are not the same, probably there is some input data that is not the same. Maybe the cell thickness, perhaps.
No, because my all values for the output on the left column, so the first output column
It's the same.
Are the same. All values I have got the same as yours.
Okay. Okay. But in this part, you get something different.
Yeah, completely different. So my
Okay.
porosity is 5 raised to the power minus 4.
Okay. Okay. Well, I will have to check that. Maybe you can maybe you can save this part in another spreadsheet, and maybe you can send me that to see what
Yeah,
could be the issue. Okay.
yeah,
And
I'll
then
have a
we can
look.
understand.
I'll have a look. Yeah, thank
Okay.
you.
Okay.
Thank
Yeah. Sure. Thanks. So that's how you would use this, and we use this spreadsheet in actual projects. I mean, it may look like a toy, but the other option that you have, as I said, if you want to do this, is to build a full DFN for that cell, and then do the auto scaling inside, let's say, Fragment, and that is a very tedious process, and it takes a long time. Okay, so then we go to number 3. Number 3 is that we assume we build this P32, and we're going to assume that normalized P32 in the well is 0.6 in the model. We assume that it's 0.6. But then what we see here is that the P32 is 0.822. So it's not what we are measuring for that cell. So we need to do something we need to apply a multiplier to that cell, that if we only have one well, we apply the same multiplier to the whole model, and then we are kind of calibrating the whole model at least to 1 point. If we have more, then we use more points. But let's do it with one cell now. So the question is, okay, if this is 0.6, well, I have to convert this 0.8, basically, that I'm modeling, or I'm sorry, I have to convert the 0.6 that I'm modeling in the grid into this 0.822, which is the number that is supposed to be in that cell. So I'm going to go to the solutions page here. So what this is the 822 that we get, and then the multiplier will be simply this P32 that we are estimating from the spreadsheet versus divided by the P32 that we get from the grid, and then this will be your multiplier. Okay, so if you multiply, let's say at this point, the whole grid by this number, then it will have units that at least are consistent with the fracture geometries that you're measuring. Okay, so here then you have a model that by changing the apertures, you are consistent with the permeabilities that you're measuring, and also by changing the P32 in your initial model is also consistent with the actual number of fractures that you are measuring at that cell. Okay. Again, if you have other cells, then you repeat the whole process for other cells. And typically what you have to do is maybe interpolate and create these smooth global multipliers for different areas of your reservoir. Okay, so that is basically it. Well, another thing that then this is the exercise, but then you can use the spec sheet to experiment yourself to understand how complex this can be. So, for instance, let's add a third family of fractures here. Let's put, for instance, 20 fractures here at 90 degrees, and then when you do that, you start understanding the effects of having different fractures families, having a stress at the same time. And then you see here that here are the two families here in blue, one at 90, one at 130 degrees, one at 40. And then when you apply the auto upscaling equation, what that tells us is that combination of stresses and fracture orientations, they will result in a Kmax that doesn't follow any of the fractures, Okay, it doesn't follow the dominant, it doesn't follow the smallest. It's kind of an average of the two dominants, somewhere there. It's close. This little blue dot here is the maximum horizontal stress. So you can change that. You can put that, let's say, at 30 degrees, and then you start gaining these complex combinations that then is that what tell you is that it's very hard to predict what will be the orientation of the flow when you have different families of fractures, when you have stresses on top of that, when you have different apertures. And this is what a spreadsheet allows at least you to explore. If we put here 140, for instance, and it doesn't change much with respect to other cases. So you can play with this with your own scenarios. There is an assumption here that that these fractures are vertical. So there are simple assumptions behind this spreadsheet, but it can give you an idea of the how complex these relations can be.